study of origins, origins of all kinds, right across the board, from the origin of the universe to the origin of life to the origin of everything you can think of. What an amazingly exciting initiative to get started at a university. I'm delighted that Lawrence is talking to us today. Please welcome him.
Thank you. Can you hear me now? Can you hear me now? Okay, good. Thanks, Richard. Actually, let me just say that my friendship with Richard has been a unique one in many ways, but one that's caused me every time we're together to think about things slightly differently. I hope mutually, and a true pleasure and honor to be here. Richard asked me to talk about cosmology, and I originally I talked to Liz Cornwall, who was organizing this, and told her what I was going to talk about, and gave her several titles, and she thought they were too depressing, so she said, why don't you just make it We're All Fucked? But I decided not to use that title. I put this quote up here. Well, I like to have quotes for when I'm being introduced, so people have something to read. But it's kind of useful, I think, because I'm going to talk about our modern picture of cosmology and how it's changed our view of the universe, the past and the future. And in some sense, how that picture is clearly remarkable, and far more remarkable than the fairy tales that are made up in most religious situations. But the key point is mystery. That's one of the things that makes science so special, I think, is that scientists love mysteries. They love not knowing. That's a key part of science. The excitement of learning about the universe. And that, again, is so different than the sterile aspect of religion, where the excitement is apparently knowing everything, although clearly knowing nothing. Now, in any case, so that's one of the reasons why I put this quote up here. But I am going to talk to you about a mystery story. So now I live in Phoenix now, and people know what these are. I used to live in Cleveland, and then I had to tell people these were stars. And this is a picture of a globular cluster, and it's a beautiful thing on a nice, clear night. But what I want to talk to you about is how our picture has changed of the universe so much that the really important stuff in the universe is not the stars and galaxies, but the stuff you can't see, the mysterious stuff that dominates nature. Okay, so it's a mystery story, so let's begin. It was a dark and stormy night, and Einstein had just developed his general theory of relativity in 1916, and an interesting time, because he had developed that theory, which was the first theory of not just how objects move through space, but how space itself could expand and contract and be dynamical. A remarkable theory that told us that space curves in the presence of matter. And it was beautiful, and he kind of knew it was correct. But at the time, it disagreed with observation, which used to bother physicists in the old days. And the observation was that the universe was static and eternal. That was the conventional wisdom in science at the time, that the universe had been around forever and would be around forever. And his theory didn't agree with that, because his theory of general relativity suffered from the same problems that Newtonian gravity suffers from. Gravity sucks. It always pulls. It never pushes. And if you put stars and galaxies out there, they will not just stay there. Gravity will produce a universal attraction that will pull them together. And so he tried to figure out what to do, and he was able to change his theory slightly, consistent with the mathematical symmetries that allowed him to develop it. So I want to just show you how he did this. So I have his equations, which is a good thing to do at 9:45 in the morning or whatever. But I do have them in a user-friendly fashion here. Okay. This is for the biologists. No, I'm just joking. So it's not completely facetious, because the left-hand side of Einstein's equations tells you about the geometry of the universe, how things are curved in the presence of the source of curvature, which in this case is the energy and momentum of the universe. So that's fine, and in fact I'm a theoretical physicist, so I have to write the actual stuff, the Greek letters. That's much more illuminating to you, I'm sure. So this was the theory that didn't work, that explained the universe we didn't live in, or so he thought. And so he was able to change it a little bit by adding an extra term to the left-hand side, which he called the cosmological term. This term on the left-hand side would produce a small repulsive force throughout empty space, so small that it wouldn't affect the Newton's laws, which of course describe beautifully, or developed in fact to describe the motion of the planets around the sun, and you wouldn't want to destroy that. So it's so small you'd never measure it in the solar system, but it could build up on the scale of galaxies and hold galaxies apart. And so that's how he thought he'd save his theory. Now, shortly after he introduced this term, it became clear that it was a problem. And in fact, here's a postcard I got when I was on leave once in Switzerland, in Zurich, and it's from Einstein to Hermann Weyl, who's a very famous mathematical physicist. And it's in German, and some of your German is better than mine, but this basically says, it's already 1923, and he's already saying, if you get rid of a quasi-static universe, then out with the cosmological constant. Because he realized that if the universe is really expanding, which is what we now know, and I'll talk to you about how we know that, then you don't need a cosmological constant anymore. If the universe is expanding, gravity can be universally attractive and just slow the expansion. And the big question of 20th century cosmology became, is there enough gravity to stop the expansion? How will the universe end? Will it end with a bang or a whimper? Will it end with a big crunch, the reverse of the Big Bang, or will it expand forever? In fact, and that's the reason why I, as a particle physicist, got involved in cosmology, because I wanted to be the first person to know how the universe would end. It seemed like a good idea. And you'll see where that came from. But anyway, so in 1923, Einstein said, you know, I wish I hadn't put it in, and threw it out, but it was really not 1923, but 1929, when we really knew the universe was expanding. And this is the person who convinced us. This is someone, and I always say this, so some of you may have heard me say this before, but it's true. This guy always gives me faith in humanity. This is Edwin Hubble. And he began life as a lawyer and became an astronomer. And so there is hope. And he made many discoveries, and I think because I'm a little short of time, I won't talk about one of the ones he made, but the biggest one he made, of course, was the discovery that the universe is in fact expanding, and it changed everything. And this is what he discovered. Now, these are not sperm, these are galaxies. These are, again for the biologists, so our galaxy is here, and when we look out, we see what he discovered was that all other galaxies are moving away from us on average. And those that are twice as far away are moving twice as fast. Those that are 3 times as far away are moving 3 times as fast, etc. And so, and we codify this saying velocity is proportional to distance. And now, what does this tell you? Okay. Well, it obviously tells you we are the center of the universe. Okay. And actually it doesn't. And in fact, my wife reminds me of that on a daily basis. And it really means is that the universe is expanding uniformly in all directions. Now, why does this ridiculous observation that where everything is moving away from us tell us that? And I've spent a lot of time trying to think of different ways to explain this, none of which have been particularly satisfactory, but I think the only way to understand it is to get outside the universe. We're in California, it's easy to do that here, but let me do it this way. Here's a universe that's two-dimensional, and that you can stand outside of, and I've put the galaxies at nice uniform distances here, and again here, and you can see at a later time the universe is bigger. The galaxies are a little bit further apart. So if you were standing outside of that universe, it would be obvious that it was expanding uniformly in all directions. Now, what would you see if you were on that universe? Well, just pick a galaxy, any galaxy, and the way we could figure out what you'd see from that galaxy is to superimpose this image on top of this one, placing this galaxy on top of itself. Okay, what do you see? You see precisely what Hubble saw. Every galaxy is moving away from this galaxy. Those that are twice as far away have moved twice the distance in the same time. Those that are 3 times as far away have moved 3 times the distance. And it doesn't matter which galaxy you're on. Everywhere you see the same thing. Everywhere you think you're the center of the universe. So depending upon your mood, either every place is the center of the universe or no place is the center of the universe. It doesn't matter. The universe is expanding. And that really did change everything. And by the way, it had profound religious implications, at least. As some of you may know, that in response to this and other things, the Pope at the time gave an encyclical that science had proved Genesis. And the interesting person, the first person to actually show there had to be a Big Bang, was a Belgian priest who was also a physicist named Georges Lemaitre. And the really interesting thing about Lemaitre is when the Pope said that, Lemaitre wrote him a letter and said, "Stop saying that." Just really amazing for a priest, because he said this is a scientific theory. You can take it if you believe in God and believe in Genesis to validate your beliefs. But you can also take it to mean that, in fact, the laws of physics take us right back to the beginning of time without God. What you take from it depends upon your religious and metaphysical beliefs, but whatever you say, the Big Bang happened. And I think that's if we could just convince a lot of people of just that simple thing, that the universe is the way it is, whether we like it or not, I think we'd overcome a lot of problems in this country, and I have to waste far too much time on that. But anyway, okay, but this is a science talk, although I'll throw in little bits of commentary throughout, I suppose. How do we know the universe is expanding? It's such an important thing, I want to spend a few minutes on that. Well, we do as these two guys on the plane out there near Arizona say to one another, I love hearing that lonesome wail of the train whistle as the magnitude of the frequency of the wave changes due to the Doppler effect. Now, what they're pointing out is that when a train comes towards you, the train whistle sounds higher. When a train moves away from you, the train whistle sounds lower. And that same principle was used by Hubble and others. The same is true for light for very different reasons. So when we look at distant galaxies, if they're moving away from us, the light, which is a wave, gets stretched out. The longer wavelength part of light, or the red end of the spectrum, so it's called redshifted. And galaxies are more and more redshifted the further and further they are away from us. So that's how we know their velocity. The velocity is easy. How do you know distance? That's really hard. The universe is a big place. And we don't have tape measures that are that big. We have to find a way of determining distance without actually going to a place, and that's hard. And in fact, one of the ways, well, of course, the way we do it is we use physics. We could determine the distance to the back of the room if I turned out all the lights and only one light was on and I knew it had a 100-watt light bulb by having an old-fashioned camera, which none of us have anymore, that had a light meter on it. And if there were 100 watts there and I was receiving 1 watt of light here, I know how that light spreads out as 1 over the square of distance. And so I could determine by how much wattage I was receiving here, knowing the wattage of that light bulb, how far away it was. Okay? This undergraduate or high school physics exercise. The problem is the universe isn't full of 100-watt light bulbs. If it was, life would be easier. So we have to try and find the equivalent. We have to try and find what's called a standard candle. Something whose intrinsic brightness we understand, and therefore when we look at it through a telescope, we see how bright it appears through the telescope, and we work backwards to figure out how far it is. That's the hard part. That's why it's been so hard to determine the rate of expansion of the universe, because it's hard to find standard candles. This is Hubble's original data from 1929. And this is one of the reasons he was such a great scientist, because he knew to draw a straight line through this data set, which itself is already not so clear. It's not obviously the right answer. But what he found was, in fact, that velocity is proportional to distance. Okay? And the great thing is he got the answer wrong by a factor of 10, which was an embarrassment at the time. Again, I'll throw a little commentary in it. Because if the universe were expanding this fast, you could calculate its age, and its age would be 1.5 billion years old. That was in 1929. Now, as anyone knows, if you read any of Richard's books, you would know that, well, by 1929, we already knew the Earth was older than 1.5 billion years old. And so it was embarrassing that the universe was younger than the Earth. One of the many embarrassments in cosmology that's happened over the years. And in fact, taken by some people to once again argue that science didn't know what it was doing. But the problem was, of course, he wasn't a bad astronomer or a bad scientist. The problem was trying to measure distance, because he didn't have good standard candles. And that's, as I say, been the holy grail, if you wish, of cosmology over the last century. And we now have standard candles. Here's one. I wish there was better resolution on this projector. It's a beautiful picture from the Hubble Space Telescope of a distant galaxy far, far away and long, long ago. And there's a whole galaxy. It's about 1 billion light years away. We're looking at it as it looked 1 billion years ago. So many of those stars no longer exist. And here's an object that's just as bright as the whole center of the galaxy. You'd think it's a star that's near in our galaxy that just got caught in the picture frame. It's not. It's a star on the edge of that galaxy that has exploded. And exploding stars shine with a brightness of 10 billion stars. They're the brightest fireworks in the universe, supernovae. And they're remarkable, and I keep having asides. Maybe I'll get to my point eventually. But this is something that I wrote a whole book about, and someone asked me yesterday why I wrote that book. Because it is the most poetic thing I know about the universe. Richard wrote a great book called, what's it called? Our Ancestors? What's it called? Ancestor's Tale, yes. I wanted to make sure I got that right. And I wrote a book that was a different Ancestor's Tale. It was called Adam. But the amazing thing is that every atom in your body came from a star that exploded. And the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust. You couldn't be here if stars hadn't exploded, because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution weren't created at the beginning of time. They're created in the nuclear furnaces of stars, and the only way they can get into your body is if the stars were kind enough to explode. So forget Jesus. The stars died so that you could be here today. Okay? And anyway, this is great. Anyway, so the point of, the real point of reason I showed this picture is that these objects, these exploding stars, are great standard candles. We can actually observe them amazingly, even though only one occurs every 100 years per galaxy. There are enough galaxies that if you put your hand up in the night away from LA and looked in a dark spot in the sky and made a hole the size of a dime, with a large enough telescope you could see 100,000 galaxies. And that means that even though stars explode once every 100 years per galaxy, in that little region with 100,000 galaxies, on a given night you'll see 10 stars explode. The universe is huge and old, and rare things happen all the time, including life. And so it's an amazing thing. And we can observe stars exploding, we can measure their brightness, we can measure their colors, and that has allowed us to produce a great standard candle. And after 75 years, we now can determine the expansion rate of the universe. This is a new Hubble diagram, much better than Hubble's. It was made after the discovery that on a log plot everything is a straight line. But even still, we now know the rate of expansion of the universe to 10%, not a factor of 10. And we therefore, in fact, we now know the age of the universe through other things extremely accurately, to almost 4 decimal places. 13.72 billion years is the age of the universe. It's amazing that we can say that with a straight face and have scientific reasons to support that. Okay, great. So let's go back to Einstein. Einstein had this cosmological term. He said, "It was my biggest blunder. I want to throw it out, get rid of it." But the problem is you can't get rid of it so easily. Because using the miracle of modern mathematics, you can rewrite that equation. And now this is a small step for a mathematician, but a giant leap for a physicist. Not because it's that hard to put this term over there. Most of us could do that. But because it now represents something very different when it's on this side of the equations. Here it was somehow a geometric quantity. When it's here, it looks like a new contribution of the energy and momentum of the universe. What could contribute a term like this? And we know the answer. Nothing. By nothing, I don't mean nothing, I mean nothing. If you take empty space, and that means get rid of all the particles, all the radiation, absolutely everything, so there's nothing there. If that nothing weighs something, then it contributes a term like this. Now, that sounds ridiculous. Why should nothing weigh something? Nothing is nothing. And the answer is nothing isn't nothing anymore in physics. Because of the laws of quantum mechanics and special relativity, on extremely small scales, nothing is really a boiling, bubbling brew of virtual particles that are popping in and out of existence in a time scale so short you can't see them. Now again, that sounds like philosophy, like counting the number of angels on the head of a pin, or religion, or something useless. I shouldn't say, Dan Dennett is here, I shouldn't say philosophy is useless, but anyway, he's also a friend. But the point is, we can't measure virtual particles directly, but we can measure their effects indirectly. And in fact, they're responsible for the best predictions in physics. Here, by the way, is actually an animation that was shown at the Nobel Prize ceremonies about 5 years ago by a friend of mine who happened to win the Nobel Prize for developing the theory that produced this. This is the space inside of a proton, the empty space inside of a proton. Not where the quarks are, but the empty space between the quarks. And this is an animation, but it's an exact animation coming from physical calculations. This is what the space looks like. Now, how do we know that? Well, there are a lot of reasons, but one of the things are, it turns out most of the mass of the proton comes not from the quarks within a proton, but from the empty space between the quarks. These fields popping in and out of existence produce about 90% of the mass of a proton. And since protons and neutrons are the dominant stuff in your body, the empty space is responsible for 90% of your mass. So these empty space is vital to science, and these calculations are vital to understanding not just protons, but electrons and atoms, and produce the best comparisons, and I will repeat this, the best comparisons between theory and experiment in all of science. To 10 decimal places in quantum electrodynamics, using these calculations, we can get the right answer. It's amazing. So, if that's the case, let's calculate the energy of nothing where there's nothing else. And when we do that, we come up with a calculation which is pretty bad. It's the worst prediction in all of physics. We calculate, you can't even see it, I think, there's a 1 at the end of that. We calculate that the energy of empty space is a gazillion times the energy of everything we see. That, as I say, is the worst prediction in all of physics, which is why we didn't talk about it for a long time. We calculate that empty space should have an energy of 120 orders of magnitude more than galaxies and stars and people and aliens and all the rest. And if that were the case, we just wouldn't be here. So we knew something was wrong with this calculation. It's been around since I was a graduate student. And we knew what the answer was. Theorists always know the answer. They're just sometimes right. We knew the answer was 0, because it's the only sensible answer. Because, you know, you can't cancel a big number like this. Let's say the energy of empty space was comparable to the energy of everything we see. Well, we'd have to cancel this big number to 120 decimal places and leave a finite answer in the 121st decimal place. No one knows how to do that in science. But 0 is a number we can get beautifully in science. We use mathematical symmetries. Things cancel, equal and opposite things cancel all the time in science because of symmetries of nature. So we knew the answer. We didn't know what the symmetry was, but we knew the answer was 0. And we could go to bed at night and that was fine. But you know, the neat thing about cosmology is it's really a science. And science is empirical. Knowing the answer means nothing. Testing your knowledge means everything. And so the question is, we should test what the energy of empty space is. And how can we do that? Well, we weigh the universe. How do we do that? We stand on the shoulders of giants. This is a picture I took in an island off Sweden, which used to be an island off Denmark now, which used to be an island off Sweden. It's the island of Ven. I think I said that right. And this guy, if you look carefully, he doesn't have the end of his nose. His name is Tycho Brahe. And he, as many of you know, laid the basis for Newton's law of gravity by doing nothing other than spending 20 years on his back, a noble tradition, in this case, looking up at the sky without a telescope, measuring the positions of the planets around the sun. And then he was a crummy feudal lord. He got kicked off that island. He gave the data, went to Prague, gave the data to a hapless assistant named Johannes Kepler, who again spent 20 years without a Macintosh trying to interpret the data, and fudged it, we now know, and came up with, of course, Kepler's laws, which led to Newtonian gravity. And the point is, we can use gravity to weigh the universe, including the weight of empty space. Now, why do we care? The reason I got into cosmology. General relativity tells us that space is curved, and therefore the universe can be a one of 3 different geometries: open, closed, or flat. Now, I can't draw pictures of 3-dimensional curved universes very well, so here are pictures of 2-dimensional curved universes. This is a closed universe, a sphere, a surface of a sphere in 2 dimensions. But if we had a closed 3-dimensional universe, it's very simple. It'd be very similar. If our universe was closed, if we looked far enough in that direction, we would see the back of our heads. Light would go around the universe. And an open universe would be infinite in spatial extent, as would a flat universe. And that sounds really nice, but it's irrelevant. The really important thing is, in a universe full of matter, a closed universe will expand and stop and then recollapse in a big bang, in a big crunch, the reverse of the Big Bang. An open universe will expand forever, and a flat universe will expand and slow down but never quite stop. And that's why we wanted to know which universe we live in. And as I say, that's why I wanted to learn about it, because once I knew which universe we lived in, I would know how the universe ended. Okay? And so, weighing the universe tells us what the curvature of the universe is, and that's why we want to weigh it. So here I want to just show you in the next few minutes how, in fact, some of the most remarkable developments in cosmology, and then tell you how they completely changed our picture of the universe so that we understand that the universe we live in is the worst of all possible universes to live in. Okay, just so you know where we're heading. This is a cluster of galaxies. Each dot in this picture is a galaxy. Again, amazing to think about. Remarkable. Every one of these galaxies contains hundreds of billions of stars, and perhaps civilizations, some civilizations that are mired in religious gunk, other civilizations that have moved beyond, and other civilizations that are long dead, because this is about 3 billion light years away. 3 billion years ago is when that picture was taken, basically. Now, clusters of galaxies are the biggest bound objects in the universe, so if we could weigh them, we could weigh all the mass in the universe, and we can weigh them now. We can weigh them by using general relativity. Because in this picture is a remarkable phenomena that Einstein first predicted in 1937, though he said it would never be observed. He underestimated observers. If you look at this picture, you'll see these blue things, these weird blue things. That is a phenomenon that we now understand as gravitational lensing. Einstein told us that a mass will curve space around it. And he realized, therefore, if you had a big enough mass and you have a source of light behind that mass, the light can bend around that object and come back and be magnified, just like my glasses magnify things. Or, like a cut glass goblet, if you look through it, I'd see many images of this room. Mass can act like a lens and magnify things and split images, and that's precisely what we're seeing. All of these blue things are different images of a single galaxy located about 3 billion light years behind this cluster. Gravity is magnifying the image, distorting it, and bending it. Remarkable. Truly remarkable. But because we understand general relativity, we can work backwards and figure out how much mass must be in that system and where it is in order to produce that image. We can weigh the system using general relativity. And when we do that, here's an inversion by Tony Tyson, who's now up in Davis. This is the system, and the spikes are where this is where the mass is in this system. The spikes are where the galaxies are. But you notice most of the mass in this whole system of clusters of galaxies is not where the galaxies are. It's between the galaxies. It's where nothing is shining. About 50 times as much mass in this system, and in all systems we can measure, comes from stuff that doesn't shine. And physicists, with their linguistic perspicacity, have called it dark matter. And we now understand that 90% of the mass of galaxies and clusters, including our own Milky Way galaxy, is made of stuff that doesn't shine. And that isn't maybe that exciting, because there's lots of things that don't shine. You don't shine if I turn the lights out. Well, those of you from Los Alamos might, but the rest of you don't. But so it could be snowballs or planets or boring stuff, but it can't be. Because for reasons I don't have time to explain, we know how many protons and neutrons there are in the universe. We can actually measure that. And there aren't enough to make up all this dark matter. So we are pretty convinced that that dark matter is a new type of elementary particle. Something that doesn't normally exist on Earth. And the great thing about that is that means the dark matter isn't just out there, it's in this room. As you doze off, it's early in the morning during this lecture. It's going right through your body. And that means we can do experiments here on Earth to look for it, which is remarkable. And in fact, I'll show you an experiment in a second. But by measuring the mass of these systems and this dark matter, taking normal matter plus dark matter and weighing it, we now have determined how much stuff there is in the universe. When physicists have an important number, they give it a Greek letter all the time. So we call it omega. Omega is the ratio of the total amount of stuff we know is in the universe divided by the amount of stuff you need to make a flat universe, the boundary between an open and closed universe. If it's less than 1, the universe is open. If it's greater than 1, the universe is closed. And we have now measured unambiguously that there's only 30% of the amount of material in the universe, including dark matter, to make the universe flat. Okay, we'll come back to that in a second, but I just want to show you that we actually do things in physics. This is an experiment to look for dark matter. It's a boule of germanium. And there are experiments like this all around the world, in mines, deep underground, because you want to shield out cosmic rays, because there are lots of them going through your body right now. You want to only see the dark matter, and the dark matter particles on average will go right through the Earth, we think, because they don't interact strongly. And most of the time right through this detector, but every now and then one of them will bounce off an atom, the nucleus of an atom of germanium. Heating, and the first thing we do is we cool this thing down to 1/1000th of a degree above absolute zero, which can easily be done nowadays. And if one of these dark matter particles bounces off a nucleus of an atom, it'll heat the whole thing up by 1/1000th of a degree. And we can measure that. And there are experiments here in South Dakota and in Europe, all over the world, looking for dark matter. We haven't found it yet. The other exciting possibility, which I should really indicate, which is one of the reasons people are very excited this year, is we may not have to wait for the universe to give us dark matter. The Large Hadron Collider, which is turning on this next month in Geneva, before it creates a black hole that will kill us all, we think actually might, by recreating the early conditions of the early universe, create the very particles which were last created at the beginning of time. So we may first see the dark matter by creating it in Geneva. It's a race. Okay, but to go back to this number here, this is a real problematic number. We now know the universe has only 1/3 the amount of matter to make it flat. The problem is that theorists like me knew the answer. The universe must be flat. Why? Well, there are two reasons. There's the one I normally say, which is it's the only mathematically beautiful universe, which is true. But there's another reason I don't usually talk about, but I'll talk about here. It turns out that in a flat universe, the total energy of the universe is precisely 0. Because gravity can have negative energy. So the negative energy of gravity balances out the positive energy of matter. What's so beautiful about a universe with total energy 0? Well, only such a universe can begin from nothing. And that is remarkable. Because the laws of physics allow a universe to begin from nothing. You don't need a deity. You have nothing, 0 total energy, and quantum fluctuations can produce a universe. So if the universe isn't flat, we're worried, because then you've got energy at the bigger beginning of time. So that was another reason that people like me were pretty sure the universe was flat. But the damn observers came up with the wrong number. Well, this is a really crummy way to measure the curvature of the universe. Why don't we measure it using geometry directly? So we can measure the curvature of the universe. And to do that, I want to ask you, how would you measure the curvature of the Earth if you couldn't go outside the Earth and see it from a satellite, or you couldn't go around it? Very simple. You draw a triangle, and you ask a European high school student, what's the sum of the angles in a triangle? And they'll tell you 180 degrees, but you say, that's fine, you learned your geometry from Euclid. But on a curved surface, it's very different. On the surface of the Earth, I can draw a triangle that's very different. I can go along the equator, I can make a right angle, go up to the North Pole, make another right angle, and come back to the equator, and I have a triangle with 3 right angles. 3 times 90 is 270. So if I made a big enough triangle on the surface of the Earth, I could measure the curvature of the Earth. I wouldn't have to go around it. Now it turns out, even though this is a 2-dimensional picture, the same is true for a 3-dimensional curved universe. If I had a big enough triangle, and I measured the angles in a triangle, I could measure the curvature of space. And we've been able, in the last decade, to find a big enough triangle. And I want to spend 5 minutes telling you about that. Because it's the most important, probably, observation in all of cosmology. The observation of the cosmic microwave background radiation, the afterglow of the Big Bang. One of the many reasons we know the Big Bang actually happened. What do? When we look out at space, we look at galaxies that were, say, 1 billion light years away, and they're 1 billion years ago. But if we know the universe is 14 or 13.72 billion years old, if we look far enough, we should see the Big Bang, right? Well, we can't see all the way to the Big Bang, because between us and the Big Bang, there's a wall. So like this wall here. Not really hard like that, but the fact the wall is opaque means I can't see past it. If I go looking back in the universe, it was getting hotter and hotter and hotter, and at a time when it was 100,000 years old, the temperature of the universe was 3,000 degrees. Slightly warmer than Phoenix this week. And at that temperature, the radiation is hot enough to break apart atoms, hydrogen in particular, and break it apart so the protons and electrons are separated. You have a charged plasma, and a plasma is opaque to radiation. So we can't see back past this time, simply because the universe is opaque. But that's okay. The reason I can see that wall is that light bounces from those lights there off the atoms on the surface of that wall, is re-radiated, but the air is transparent, so I can see all the way to the wall. If we run this film forward, as the universe is opaque, 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 and then it becomes neutral, the atoms, protons capture electrons, neutral matter is transparent to radiation like this, And that means I can see all the way back to that radiation coming at that surface. A prediction of the Big Bang is there should be radiation coming at me from all directions, coming from that surface called the last scattering surface. It was 3,000 degrees then, it's 3 degrees now, and it was the radiation that was discovered by accident in New Jersey, of all places, by two people who didn't know what the hell they were doing. And they won the Nobel Prize anyway, because they discovered the afterglow of the Big Bang. Actually, another aside, I can't help this because this is amazing, and if you ever want to convince skeptics, you won't ever convince people of this who don't believe it anyway, but you've all seen this radiation. Or at least those of you who are old enough to be as old as me, before cable TV. Remember when the TV stations used to end? And then there'd be static? 1% of the static on your TV screen is radiation from the cosmic microwave background. So you've all seen it. Okay? But it's amazing, we didn't even know about it until 1965. Okay? It was, in fact, it had been predicted by people like George Gamow, but people had forgotten that. In any case, as interesting as that history is, on this surface is a very important scale, 1 degree. Why 1 degree? Because that represents a distance of 100,000 light years. Now, this surface existed when the universe was 100,000 years old, and Einstein tells us no information can propagate faster than light. So that means nothing that happened over here at that time could ever affect anything that happens over here. But more importantly, if I have a lump of matter that's this big, it knows it's a lump of matter, so it starts to collapse. But if I have a lump of matter that's this big across at that time, it doesn't even know it's a lump, because gravity can't have traveled across it. So it's like Wile E. Coyote in those cartoons when he goes off the cliff. He waits a while before he collapses. Okay? And such large lumps won't collapse. So the biggest lumps that can have collapsed at that time will be 1 degree across, and that gives us a cosmic triangle. Because we have a ruler that's 100,000 light years across, the size of the largest lumps, a known distance away from us, and in a flat universe, light rays travel in straight lines, and we can calculate the angle on our eye subtended by a 100,000 light year across ruler at that distance. It's 1 degree. In an open universe, light rays diverge as you go back in time, and the whole thing might be ½ a degree. The ruler will look smaller. In a closed universe, light rays converge as you go back in time. The ruler will look bigger. So we just have to look at that microwave surface, try and measure the lumps, and see how they 1 degree, ½ a degree, or 2 degrees. We've been able to do that in the last decade. This was the first experiment that did it. It was called the boomerang experiment in Antarctica. It was a balloon, took this microwave radiometer above the Earth's surface to look at this radiation, take a picture of it, and this balloon went around the world, which is easy to do in Antarctica, okay? And it took a picture. It's really easy in the South Pole, you just do this, but anyway. And this is the image, well this is a false color image of that, I put it, superimposed it on the original image. This is the image of the microwave background, the hot spots and cold spots in the microwave background, and these are the lumps in the early universe. And the question is, how big are they? And here's a different false color image of the same region, and we can compare this with universes we create on computers. Here's a closed universe, where the lumps are bigger. They should be this big across. If they're 100,000 light years across, they should look that big. Well, that's bigger than these lumps. Here's an open universe, and you can't see the resolution of the screen isn't that good, but the average size lump is about that big. Smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. In fact, it's right now, we know, to an accuracy of better than 1%. The universe is flat. It has zero total energy, and it could have begun from nothing. And I've written a piece, although of course I got a lot of hate mail, saying that in my mind this answers this crazy question that religious people always keep throwing out, which is, why is there something rather than nothing? The answer is there had to be. If you have nothing in quantum mechanics, you'll always get something. It's that simple. It doesn't convince any of those people, but it's true. Now, great, we know the universe is flat. But if you've been awake, you realize, 10 minutes ago I proved the universe was open. There's only 30% of the stuff in the universe needed to make it flat. Where's that other 70%? Well, if you put energy in empty space, so empty space weighed something, you wouldn't see it. It's the empty space between the galaxies. You're far away from the galaxies, you wouldn't see it. But what would that empty space do if you put energy in it? Well, it produces a cosmological constant. That would cause the expansion of the universe not to slow down over time, as any sensible universe should do, but to speed up over time. In 1998, people measuring these supernovae at large distances to measure the Hubble diagram tried to see what was happening at large distances to see if the universe was slowing. Well, they all knew the universe was slowing down. They wanted to measure how much. This doesn't look like much, but it was a revolution in cosmology. I can draw a straight line through that data set there and bring the whole thing down and make it horizontal. And if the universe was slowing down, these distant supernovae should have followed this curve. Much to the surprise of the observers, the supernovae lay above the straight line. And the only way to explain this, well, there's two ways. Either the data is wrong, which it usually is, or the universe is accelerating, speeding up. And if just for fun one believed it was speeding up and asked how much energy would you have to put in empty space to make it speed up by the amount we measure it, it's exactly the amount we are missing. Everything holds together. Our new picture of cosmology is that we live in a universe dominated by nothing. The largest energy in the universe, 70% of the energy in the universe, resides in empty space. And we don't have the slightest idea why it's there. Now, that's what I just said. Let me also put an aside before I get on to the rest in the last 5 minutes of the talk. This completes, in some sense, the ultimate Copernican principle. Copernicus told us we didn't live in any place special. We now know two things. Well, one thing. I'll tell you the second one in a second. This tells us that we are more insignificant than we ever imagined. If you take the universe, everything we see, stars and galaxies and clusters, everything we see, if you get rid of it, the universe is essentially the same. We constitute a 1% bit of pollution in a universe that's 30% dark matter and 70% dark energy. We are completely irrelevant. Why such a universe in which we're so irrelevant would be made for us is beyond me. Okay, good. Now I wanted a little bit of applause. Now we can go back to the science. What I really want to spend in the last few minutes is telling you is how it's changed our picture of the future. In science and the picture of the universe. It has changed our picture of the future completely. And I'm going to rush through this, so let me give you the short answer first. Kurt Vonnegut has claimed as having said this at a private girls' school when he gave a commencement address. I've given 2 commencement addresses, and I've never had the guts to say it, but I'd love to. He said, things are going to get unimaginably worse, and they're never, ever going to get better again. This was before the Bush administration, too, in fact. But that's our understanding of the universe. I want to tell you about it briefly. I want to tell you about a few things that you'll hear about, and some of the things that creationists and intelligent design people promote as arguing somehow that there's design in the universe. This is one of them, and I want to explain to you why it has nothing to do with design. It is weird and strange that we live in a universe that looks like we do, because this is a brief history of time. This is the density of matter as the universe expands. It goes down as 1 over the volume. But it turns out the energy density of empty space remains constant as the universe expands. And we live today, right here, when the energy density of empty space is 3 times bigger than the energy density of matter. But when you look at this has driven physicists crazy. Because this is the only time in the history of the universe when these two numbers are about the same. At all earlier times, the density of matter was much greater. At all later times, the density of empty space will be much greater. Why do we live at this special time in the history of the universe? Well, one of the answers that's been given is that these things exist, galaxies. Why? Well, let's go back to this picture, and let's pretend the energy of empty space were 50 times bigger. Then these two curves would cross, not now, but then. Well, when is then in this case? Then is the time when galaxies first formed. But if the energy of empty space was bigger than the energy density of matter when galaxies first formed, then the repulsive force would be greater than the attractive force. Galaxies would never have formed. Well, if galaxies never formed, then maybe this is telling us something. And this has produced something that I call anthropic mania. If there are many different universes, physicists have argued, and the energy of empty space can vary in each one, then only in those in which it's not much greater than what we measure today will galaxies form. Okay? But then, only then will stars and planets form, and only then will astronomers form. So the universe is the way it is because astronomers are here to measure it. Now, it not only sounds ridiculous, but it also sounds religious. And some people have said the universe is fine-tuned. If it were any different, then we wouldn't be here. God clearly created the universe to be for us. Now, that's nonsense. And it's nonsense for the same reason that you learn so beautifully in Richard's books. Why can bees tell the colors of flowers so they can find them? Not because God intended them to do it, but if they couldn't find the flowers, they wouldn't get the stuff they needed to eat, and they wouldn't be around. It's natural selection. And what this is really telling us is kind of a cosmic natural selection. Because all it's saying, if it's true, is that it's not too surprising that we find ourselves living in a universe that allows life. Because in the universes that don't allow life, we wouldn't be here. It's just that simple. So if you wish, it's a kind of cosmic evolution. Or cosmic natural selection is a better way of thinking about it. Now, as pretty as that is, I think it's wrong. It's ugly. And it goes against everything I know about science. Science has told us the last 400 years why the universe must be the way it is, not why it has to be something different. In fact, Einstein once asked a question. He said it the wrong way. Put it here because, I wanted to quote him. He said, what really interests me is whether God, and by God he didn't mean God, had any choice in the creation of the universe. What he really meant is, are the laws of physics fixed so that if you changed one parameter, you couldn't have a universe? Or can you have infinite numbers of different laws of physics that all work, and it just happens to be the way it is? If this anthropic picture is right, then physics is really an environmental science. There's no fundamental laws necessarily. We're just here by an accident. And the laws of physics are the way they are, not because there's some beautiful mathematical theory that tells us they have to be, just because if they were different, we wouldn't be here. Now that I find repugnant, although it may be true. And I was going to spend time telling you about that, but I'm really behind, so maybe I shouldn't. Let me just say that there is a theory that suggests, in such a picture, if there are an infinite number of universes, then you don't need a theory of everything. Forget what I wrote there. You need a theory of anything. You just need an infinite number of universes and some theory that tells you anything can happen. We have such a theory, and I did want to spend 1 minute telling you about it. It's called string theory. Here's the brief summary of it. One person said to another, I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. The second guy says, okay, what would that imply? And the first guy says, I don't know. So that's a history of string theory in the last 25 years. And the point is, it is fascinating for many people, but one of the things it might predict is that anything is possible. And if anything is possible, it's not clear you have a scientific theory at all. But now I'm going to skip forward. In the last minute, I had a good joke about George Bush, but I won't give it. And I'm going to skip this. I'm going to skip this. Forgive me, it's really interesting, but I want to get to the very end, which will really tell you about how miserable our future really is. And it should give us a kind of cosmic humility, which is the other thing that should be characteristic of science. A humility, the recognition that we don't understand everything. Bill Maher talked about it last night. What pompous assholes like Rick Warren, who claim to understand everything, are an anathema to science. We should realize that where there's more we don't understand about the universe than we do. And I want to give you an example of this. The far future. What's going to happen in the far future? Remember, 100 years ago, we thought we lived in a static, eternal universe. What will the future bring? The amazing thing is, for civilizations that live in the far future, what will they see? Well, the universe is accelerating. That means all the distant galaxies are getting carried away from us, and eventually they'll move away from us faster than the speed of light. It's allowed in general relativity. They will disappear. The longer we wait, the less we will see. In 100 billion years, any observers evolving on stars around and there will be stars just like our sun in 100 billion years. Any observers on civilizations evolving around those stars will see nothing except for our galaxy, which is exactly the picture they had in 1915. All evidence of the Hubble expansion will disappear. Why? Because we won't see the other galaxies moving apart from us. So they will have no evidence, in fact, of the Big Bang. They won't see the Hubble expansion. They won't even know about dark energy, and I won't go into that. They won't know about the cosmic microwave background. It will disappear too. It will redshift away, and it turns out, for fancy reasons, there's a plasma in our galaxy, and when the universe is 50 times its present age, the microwave background won't be able to propagate in our galaxy. All evidence of the Big Bang will have disappeared. And those scientists will discover quantum mechanics, discover relativity, discover evolution, discover all the basic principles of science that we understand today, use the best observations they can do with the best telescopes they will build, and they will derive a picture of the universe which is completely wrong. They will derive a picture of the universe as being one galaxy surrounded by empty space that's static and eternal. Falsifiable science will produce the wrong answer. In fact, I want to end with the good news. We live in a very special time. The only time we can observationally verify that we live in a very special time. Okay, it's clear I'm being facetious. What it really should tell us is we've discovered this crazy picture of the universe that we don't understand at all. It all holds together, but maybe if we had evolved 5 billion years earlier, there would have been observables we could have seen that would have changed that picture. Maybe 5 billion years in the future, it'll be different. The universe remains mysterious, and that is great. But I do want to say, in the far future, this is the picture. We will be lonely and ignorant, but dominant. And those of us who live in the United States are used to that. Let me end. Okay, that's the end. Thank you. I'll leave it back. Okay, thanks. The reverse of the Big Bang, or will expand forever. In fact, and that's the reason why I, as a particle physicist, got involved in cosmology, because I wanted to be the first person to know how the universe would end. It seemed like a good idea. And you'll see where that came from. But anyway, so in 1923, Einstein said, you know, I wish I hadn't put it in, and threw it out, but it was really not 1923, but 1929, when we really knew the universe was expanding. And this is the person who convinced us. This is someone, and I always say this, so some of you may have heard me say this before, but it's true. This guy always gives me faith in humanity. This is Edwin Hubble. And he began life as a lawyer and became an astronomer. And so there is hope. And he made many discoveries, and I think because I'm a little short of time, I won't talk about one of the ones he made, but the biggest one he made, of course, was the discovery that the universe is in fact expanding, and it changed everything. And this is what he discovered. Now, these are not sperm, these are galaxies. These are, again for the biologists. So our galaxy is here, and when we look out, we see what he discovered was that all other galaxies are moving away from us on average. And those that are twice as far away are moving twice as fast. Those that are 3 times as far away are moving 3 times as fast, etc. And so, and we codify this saying velocity is proportional to distance. And now, what does this tell you? Okay. Well, it obviously tells you we are the center of the universe.
The study of origins of all kinds, right across the board, from the origin of the universe to the origin of life to the origin of everything you can think of. What an amazingly exciting initiative to get started at a university. I'm delighted that Lawrence is talking to us today. Please welcome him.
Thank you. Can you hear me now? Can you hear me now? Okay, good. Thanks, Richard. Actually, let me just say that my friendship with Richard has been a unique one in many ways, but one that's caused me every time we're together to think about things slightly differently. I hope mutually, and a true pleasure and honor to be here. Richard asked me to talk about cosmology, and I originally I talked to Liz Cornwall, who was organizing this, and told her what I was going to talk about, and gave her several titles, and She thought they were too depressing, so she said, why don't you just make it, We're All Fucked. But I decided not to use that title. I put this quote up here. Well, I like to have quotes for when I'm being introduced so people have something to read. But it's kind of useful, I think, because I'm going to talk about our modern picture of cosmology and how it's changed our view of the universe, the past, and how space itself could expand and contract and be dynamical. A remarkable theory that told us that space curves in the presence of matter. And it was beautiful, and he kind of knew it was correct. But at the time, it disagreed with observation, which used to bother physicists in the old days. And the observation was that the universe was static and eternal. That was the conventional wisdom in science at the time, that the universe had been around forever and would be around forever. And his theory didn't agree with that, because his theory, general relativity, suffered from the same problems that Newtonian gravity suffers from. Gravity sucks. It always pulls. It never pushes. And if you put stars and galaxies out there, they will not just stay there. Gravity will produce a universal attraction that will pull them together. And so he tried to figure out what to do, and he was able to change his theory slightly, consistent with the mathematical symmetries that allowed him to develop it. So I want to just show you how he did this. So I have his equations, which is a good thing to do at 9:45 in the morning or whatever. But I do have them in a user-friendly fashion here. Okay. This is for the biologists. No, I'm just joking. So it's not completely facetious, because the left-hand side of Einstein's equations tells you about the geometry of the universe, how things are curved in the presence of the source of curvature, which in this case is the energy and momentum of the universe. So that's fine, and in fact I'm a theoretical physicist, so I have to write the actual stuff, the future. And in some sense, how that picture is clearly remarkable, and far more remarkable than the fairy tales that are made up in most religious situations. But the key point is mystery. That's one of the things that makes science so special, I think, is that scientists love mysteries. They love not knowing. That's a key part of science. The excitement of learning about the universe. And that, again, is so different than the sterile aspect of religion, where the excitement is apparently knowing everything, although clearly knowing nothing. Now, in any case, so that's one of the reasons why I put this quote up here. But I am going to talk to you about a mystery story. So now I live in Phoenix now, and people know what these are. I used to live in Cleveland, and then I had to tell people these were stars. And this is a picture of a globular cluster, and it's a beautiful thing on a nice clear night. But what I want to talk to you about is how our picture has changed of the universe so much that the really important stuff in the universe is not the stars and galaxies, but the stuff you can't see, the mysterious stuff that dominates nature. Okay, so it's a mystery story, so let's begin. It was a dark and stormy night, and Einstein had just developed his general theory of relativity in 1916, and an interesting time, because he had developed that theory, which was the first theory of not just how objects move through space, but how Greek letters. That's much more illuminating to you, I'm sure. So this was the theory that didn't work, that explained the universe we didn't live in, or so he thought. And so he was able to change it a little bit by adding an extra term to the left-hand side, which he called the cosmological term. This term on the left-hand side would produce a small repulsive force throughout empty space, so small that it wouldn't affect the Newton's laws, which of course describe beautifully, or developed in fact to describe the motion of the planets around the sun, and you wouldn't want to destroy that. So small you'd never measure it in the solar system, but it could build up on the scale of galaxies and hold galaxies apart. And so that's how he thought he'd save his theory. Now, shortly after he introduced this term, it became clear that it was a problem. And in fact, here's a postcard I got when I was on leave once in Switzerland, in Zurich, and it's from Einstein to Hermann Weyl, who's a very famous mathematical physicist. And it's in German, and some of your German is better than mine, but this basically says, it's already 1923, and he's already saying, if you get rid of a quasi-static universe, then out with the cosmological constant. Because he realized that if the universe is really expanding, which is what we now know, and I'll talk to you about how we know that, then you don't need a cosmological constant anymore. If the universe is expanding, gravity can be universally attractive. and just slow the expansion. And the big question of 20th century cosmology became, is there enough gravity to stop the expansion? How will the universe end? Will it end with a bang or a whimper? Will it end with a big crunch?